Good. So I'm Keith. Hello. I just moved to Austin. I moved from New York City, where we actually do get some snow. So I'll be talking a little bit about the Milky Way and galactic archaeology, which is kind of like a snow in the sky, kind of, maybe. And so my hope is that by the end of this talk, and by the way, you can talk during my talk, you can ask me questions, you can do whatever you need to do to get at least one fact out of this talk. So my hope is that you learn something about what galactic archaeology is and what the galaxy is as a whole. So does anybody know what this is? Since you guys are going to ask me questions, I know I'm going to get grilled. It's a telescope. Does anybody know where this telescope is? It's McDonald Observatory, which is in West Texas. It's about a 7-hour drive from here, west. And so what you see in the background is the Milky Way. And so that's the galaxy that you all live in. It's where we all, started. The Milky Way is a galaxy. Galaxies are just collections of stars, dust, gas, people, cats, you name it. And it's all held together by gravity. And our Milky Way galaxy is a typical one. It's got about 100 billion stars in it. And I wish that I had $1 for every star was in the galaxy, but I don't. However, so 100 billion stars in the galaxy, and there's something on the order of billions or trillions of galaxies in the universe. That's a lot of stars out there. And a galactic archaeologist like me is interested in questions like, how did the galaxy form? How did it evolve? How is it structured? It's not like, the bread that didn't quite turn out right on the holiday. It has some structure to it. It's not just some amorphous blob that I don't want to eat. And so these questions all kind of represent galactic archaeology. So the easiest way to answer what galactic archaeology is to take our favorite galactic archaeologist, our favorite archaeologist, Indiana Jones. So Indiana Jones will go out to somewhere and try to dig up fossils or human artifacts and try to figure out how ancient civilizations have come about and how they died. I do that. I just do it with stars. And that, of course, makes Indiana Jones quite jealous. And every star you see in the night sky is a fossil for 2 reasons. The first is light travel time. So when you look up at a star, you're not seeing it as it is now. You're seeing it as it was in the past. So for example, the sun, it's about 8 light minutes or so from the Earth. So when you look up at the sun, which I never recommend you do, it's about 8 light minutes. So that means that you're seeing the sun as it was about 8 minutes ago. You're not seeing it as it is now. The galaxy is about 100,000 light years across. So if I look through my telescope at a star at the other end of the galaxy, I'm seeing that star as it was about 100,000 years ago. So that's pretty cool. The other thing is that stars, generally their chemical fingerprint, their DNA, if you will, doesn't change over the course of its lifetime. And so if I look up at a star that's 4.5 billion years old, the sun is 4.5 billion years old, I will see whatever the universe was doing in its gas about 4.5 billion years ago. So that's the reason why every star in the night sky is a fossil. And these fossils are arranged in a galaxy. And our galaxy, the Milky Way, this is what it looked like in 1795. That's not actually what it looked like in 1795. That's what people thought it looked like in 1795 by William Herschel. And the big star in the center, that orange star, is where they thought the sun was, at the center of the galaxy. And we know, of course, that's not true. We've really advanced in the last couple of centuries in terms of how we take pictures of the galaxy. And so here's an artist's impression of what we think our galaxy looks like. It's you can see that it's a spiral galaxy. That's the spiral arms in blue. And then you also see that it has a bar in the center. And so our galaxy is a barred spiral galaxy, the bar being in the center and the spirals going around the bar. Why there's a bar there, we don't really know. How the bar is structured, how it's oriented and moving, we don't really know that either. We're still trying to figure that out, and that's really the wonderful thing about astronomy is we're still trying to figure all of these things out. The sun is not at the center. It's on the outskirts in the suburbs, about 2/3 of the way out, about 28,000 light years, and it's on an orbit of about 230 million years. So if the center of the galaxy was like Austin, the sun would be at like Pflugerville. I'm still learning my Austin geography. Is Pflugerville right? I don't know. Is that the right way of saying it? Because you guys have this thing called Guadalupe that should be Guadalupe. I'm like so confused. Manchac is Manchaca? I don't know. Anyway, Beside the point, the sun is on an orbit of about 230 million years. That means that the last time the sun was in its rough current position is right around when human beings started to evolve. Our galaxy has about 5 components to it, or we think. We're still not sure. I learned that there was like 4 components when I was an undergrad. Now there's 5, and we're still trying to figure this out. There's a thin disk of the galaxy. Thin disk is where the sun is. It's like a crepe, a French crepe. The thick disk is like a thicker form of the thin disk. It formed first. And the thick disk is kind of like the fat American pancake. Then you have the stellar halo, which is all the way on the outskirts, contains most of the oldest stars in the galaxy. Most of the galactic archaeology stuff happens there. And that's where a lot of the oldest fossils are. And that is like, what is that? Like taking your pancake and putting it in deep fried batter and then frying it, like, you know, in a really unhealthy American way. And then you have the galactic bulge and bar in the center, and that's like putting butter on top of that pancake wrapped in fried batter. Anyway, that's getting away from the artist impression and cartoons. This is the state-of-the-art data of what the Milky Way actually looks like today. So you can see the galaxy has a disky plane, and the bulge is in the center where it's actually bulging out. And then you can see the beautiful, beautiful dust lanes that are held together in the galaxy as well. And does anybody know what these 2 things are down here? The Magellanic Clouds. See, these are actually other galaxies away from our own, and they have their own stars. And one of the big questions is, how did the Milky Way actually form, or how did these galaxies form? And I'm going to tell you the answer to that question. I told you earlier that we didn't know the answer to that question. I think we actually do, and it starts with this guy. No, I'm serious. It actually does. So the Greek mythological story, this all goes back to the ancient Greeks. Hey, that's suspense. It was all about the suspense. We're back. Sorry, I wanted to make sure everyone was awake. I knew that was going to happen. So the ancient Greeks believed that basically the story the formation of the Milky Way goes a little bit like this. You have Zeus, who's in the background, kind of angry, scowling a little bit. So Zeus fathers a child with a mortal woman named Alcmene, and this child is Hercules. Of course, Zeus was very fond of Hercules, but Hercules was part mortal, and so he decided that he would give Hercules to his wife Hera to nurse. And the idea was that her breast milk would give Hercules immortal powers. And the problem was he did this when Hera, his wife, was sleeping, which is not consent at all. And Hera wakes up. Hera wakes up, and she's like, what the heck? Why is there this child on me? And she pushes the child away, out squirts some breast milk, and that becomes the Milky Way. That is how the Milky Way formed. That's actually not how the Milky Way formed. I'm just kidding. So I'll give you 2 stories for how astronomers think the Milky Way formed. The first is a theory that came about in the 1960s, late 60s, called Monolithic Collapse. And the idea is you take a big-ass gas cloud. Oops, I just said ass. Shit. And then it collapses under gravity. And as it collapses, it creates stars. And that creates an elliptical or a giant spherical galaxy. And that's a pretty simple idea. It's basically take a big gas cloud and contract it from gravity. Problem is, it creates a spherical galaxy. So you saw earlier, the Milky Way is not spherical, it's a disk. So how do you get a disk out of that? You spin it. So similar to this ice skater who's spinning, there's something called conservation of angular momentum. So she starts with her arms spread out, she's not moving very fast, and she brings her arms in and speeds up. The same thing happens in the Milky Way, or at least in this idea. You take a gas cloud, you give it a small little spin at the beginning when its arms are extended, and as its arms fold in and it contracts under the gravity, it spins up into a disk, kind of like the way that you'd also make pizza. Similar idea. So that's the idea that came about in the 1960s. The new idea came about in the 70s. The second theory is something called hierarchical galaxy formation. And that's just a fancy way of saying you take galaxies and you merge them together to create other galaxies. And so the idea is you take small subgalactic units, you merge them together in a process called galactic cannibalism. And one galaxy eats another and it becomes larger. And so which of these two ideas are correct? Well, we don't really know. We're still trying to figure that out. But this is a modern simulation of how galaxies form. And essentially it forms both this monolithic collapse probably as well as hierarchical. So you have these small subgalactic units that are these small components, and they're all merging together, creating bigger and bigger systems. And one of the things you'll see at the end of the simulation is the galaxy that's being created by galactic cannibalism is actually going to produce lots of beautiful features like tidal streams and arcs and shells and all kinds of beautiful things. And so you can make a model of positions and motions and chemistry from these simulations. So you take all the physics you know, you put it in the computer like Mike does, so we'll talk about that, and you observe the simulation. And then once you observe the simulation, you can compare that with the actual data. So that's what we do as scientists. And I actually do that observational side. I'm an observational astronomer, and so this is me at various telescopes around the world over the course of the last maybe 5 or so years. And so I use data from space-based data from something called the Gaia spacecraft, which I'll talk about next, and ground-based data from McDonald Observatory and other telescopes around the world. So the Gaia mission is what I use at the moment, and it's a purely European mission. It's called the Billion Star Surveyor, and its mission is to produce the most precise three-dimensional map of the Milky Way ever attempted by human beings ever. And to do this, the tagline kind of tells you it's going to map about 1 billion stars, so the motions and positions of about 1 billion stars. So a quick quiz of the day keeps the doctor away. That's an old phrase that my Spanish teacher used to use, which I used to hate in high school. But I decided to use it here. What percentage of the galaxy will Gaia observe? So if it's 1%. I think, hint, that might be a trivia question. So this map also, once we build this map with Gaia Data, and Gaia Data is coming out now, one of the things that I want to do here at UT is actually take that data, build that map, and then color code every star by its chemical fingerprint. So I can look for how the galaxy is actually structured. And one of the reasons why the Gaia Data is so important to us is because before Gaia launched in about 2013, before Gaia, everything we knew about the galaxy in terms of precise motions and positions was based on that little circle. So this is an image of the galaxy again. The sun in representation is where that star is. Now the sun isn't actually there because this is being observed from the sun, but I'm just giving you an idea. That's about the area that we knew. Gaia is going to extend that from this to this. So that's where that billion stars are going to be coming from, and that's really what we're going to be learning a lot about the universe. So how will Gaia do positions in space? It's something called trigonometric parallax, and this is a schematic of that showing essentially that what you do is you take a picture of the star relative to a really distant set of objects in one side of the on one side of the Earth's orbit or in one part of the year. The star's apparent position relative to the more distant background stuff is in one place. 6 months later, you take another picture, it's moved. So that's probably not super clear, so we're going to do a little activity. Here's the Pleiades. If you take out your hand and extend it fully, put your thumb up like this, and blink your eyes back and forth, what you'll notice is that your thumb, in relative to the background objects, the background Pleiades, changes in position. Now do the same thing, but put your thumb really close to your face. You'll probably notice that the angle is actually much larger in position. And that's called parallax. And so actually that angle, the amount that your star changes from one side of the night sky to or from one part of the Earth's orbit to the next is inversely proportional to how far away it is. That is to say, if the angle changes a lot, if there's a very large angle, it's really close by like this. And if it changes only a little bit, it's really far away. So that's what Gaia is doing in space. And one of the things that we'll be doing is doing chemical cartography or chemical mapping of the galaxy by adding, in addition to that Gaia data, data from these telescopes that are pictured here out in West Texas. And so this, what you're seeing, is actually another way of visualizing the sun. So if you take the sun and you pass it through a prism, kind of similar to the Pink Floyd album cover, what the Pink Floyd album cover doesn't tell you is that there's dark bands that appear in the rainbow. And each one of these dark bands is caused by the absorption of an element in the atmosphere of the star. So I can tell you how much of each element is in the atmosphere of the sun just based on how wide and small those dark bands are. And that's what I'll be doing. And I'll combine that with the Gaia data to build a map of the galaxy. And that's what galactic archaeology is all about, is building beautiful maps of the galaxy and trying to figure out how it's structured and formed. And so what I want to leave you with now is what we have now, what my team has assembled up to this point with Gaia data and all of the chemical data that we have available, which is a movie that you can now see in the Hayden Planetarium in New York City, and hopefully a planetarium near Austin if I can find one. And now what you're seeing is an image in the background of the galaxy, but in the foreground what you're seeing is every star, or about 200,000 stars from the Gaia data that also have chemical abundances. And these are color-coded by the amount of magnesium in the atmosphere of the star. And so blue means the star doesn't have very much magnesium, and orange means it does have a lot of magnesium. And you can beautifully see that the outer galaxy has a very different pattern in magnesium than the inner galaxy does. And so this is something that we'll be doing here at UT over the course of the next couple of years, building maps like this and then really trying to piece together how the galaxy formed as a galactic archaeologist. So that's kind of where I want to leave you at.
Thank you, Keith, for that very excellent and graphic Greek mythology lesson at an all-ages show.
It's Christmas time.
All right, let's take a few questions. The way this will work is you raise your hands, we will call on you, you'll ask your question, hopefully one of us will repeat the question, and then Keith will answer it. Let's start with you right here.
So why is magnesium the element of choice? So why is magnesium the element of choice? That's a very good question. The quickest answer to that is that that's the first element that I chose. I haven't done all the other elements yet, and it just happened to be quite beautiful. But scientifically, the reason why is because magnesium is thought to be one of the first types of elements that come out in the universe from something called core collapse supernovae, or from very massive stars, die very quickly. They blow out a bunch of magnesium, and we were looking to see how the first set of elements that form, how those are distributed across the galaxy. So that's the reason why we chose magnesium.
How about you right here, sir?
Since we're seeing the galaxy edge on, how can we actually tell that it has spiral arms?
That's a very good question. So how can you tell that the galaxy has spiral arms since we're seeing it edge on? The answer is that, well, there's a couple of answers. Number one is that you can look at the Gaia data and you can map the galaxy through the plane. And then you can do, in a data visualization similar to this, you can actually flip the galaxy around and you actually do see spiral structure in it. But the other reason you can see this is because if you take radio data or other data where you can peer through and actually look for gas clouds, those gas clouds also align in a spiral arm. But actually that's a very good question. And in fact, when I was in New York City, we were actually arguing whether the galaxy is in fact a spiral or not, and so that's something that we talk about in our basic Intro Astronomy 101, but we're still trying to actually map out that spiral, and the Gaia data should actually help us do that quite well, is actually mapping those spirals. So where those spirals exist in terms of actually creating a better map of this in terms of the spirals, I think we'll actually, in the next couple of years, we'll actually have enough data to be able to do that properly.
All right, anyone, we'll do a balcony question and then we'll get to you. So right up here.
So you showed us a computer simulation of how these things may form by capturing, cannibalizing. Does that model produce a bar in any case?
So the model that I showed you does not produce a bar because it wasn't high enough resolution, they say. That is to say that there wasn't enough, they weren't actually going through the detailed, they weren't looking at the details of the actual galaxy itself. But some models do create bars and some don't. And the part of the point of what we're doing at the moment is trying to figure out in the simulations what creates bars and what don't, what does not, and then from there we can actually constrain the physical processes that are actually important in galaxy formation or forming a bar-like galaxy that we see. And so that's how science is done. We see a bar from observations. Now we have to go back to the modelers and say, how do you create that bar, and then interface with them in a circle and try to continue to understand what physical processes are important in galaxy formation. So this is something that we're actively doing at the moment. That particular simulation did not form a bar, but I know that there are simulations that do.
All right, and then our last question, we'll do right there.
Okay, so what prevents Gaia from mapping the other 99% of the galaxy? The first is that it's very hard to track a billion stars. Like that's actually a really, really challenging thing to do. So that's one problem, is just actually how do you map a billion stars? The second is data. So this spacecraft is out at L2 and sending back data, and it sends back data. It's the largest camera ever flown in space. It has 1 billion pixels on it. Okay, sending that data back is not even possible. There's not enough telemetry to send that data back. So they actually have to send postage stamps back because there's not enough data. There's not enough bandwidth to send the data back. So that's a second problem. And then a final problem is dust. So if you ever look at the picture of the galaxy, you'll see that there's dust intervening our view of the galactic center. That dust blocks our view of stars behind the dust. And there's nothing we can do about that. I mean, the only thing we really can do is go to the infrared and get behind the dust. And that's really hard to do. And so peering through that dust to the other side of the galaxy is really, really, really hard to do. And we're just now getting technologically available, we just now have the technology to actually do that for the first time using infrared telescopes. And so those are the three primary reasons that I can think of, at least at the moment, as to why we can't get to those other 99%. But future missions, I think, will allow us to get many more percentages worth of data. And I hope that not only we're going to get more data from our own galaxy, but I hope we'll push that to other galaxies as well in the local neighborhood. And I hope Mike will kind of explain why that's important.
All right, if you have more questions for Keith, he will be around during intermission, so make sure you track him down. Let's give another round of applause for Indiana Jones of the Galaxy.